Today we're going to begin the unit of equilibrium. We've been talking about reactions now, and we were talking about chemical reactions where you have a reactant, a yield sign, and a product. And we say that's a forward reaction. And most of the time those forward reactions will go to completion. But quite frankly, there are times where a reaction will make a product, and then all of a sudden that product will turn around and go the other direction. We say the reaction's reversible. We see this happen in what we call a closed system. And so I have an example here on the screen where I have just a container of water, and left in an open container, we know that water will evaporate, and so it'll get out of the system. So this is just physical change, and so we see equilibrium happen with physical as well. And with water, we do see some of those water molecules coming back down into that. But if I were to close the container off, and so now I would close the system is what we would call it. So those water molecules really couldn't escape. What we're going to see, because there's going to be bouncing around of these gases and these water molecules, we will see there a point where the water will start evaporating, and then it'll start condensating back into the water. And that would be what we call a dynamic equilibrium. Dynamic equilibrium is where the forward reaction, in this case water as a liquid going into a gas, and then we would see the gas turn around going back into a liquid. Now this is a physical change, but physical change can reach equilibrium as well. And we're going to see this happen with chemical reactions. And so it needs to be a closed system for this to be able to happen, so we don't get any molecules escaping to the atmosphere. And we see it quite a bit with gases in a closed system. And so we're going to start with the note page. And so there's just the vocabulary. Equilibrium, most chemical reactions are reversible. When a system comes to equilibrium, the reaction's not stopping, even though it looks like it's stopping. The fact is the forward and the reverse are at equal rates. So we, in our eyes, because our eyes can't really see down on the molecular level, we can't see that there's something changing, but there really is a change going on. It is making reactants, it is making products, and then the products are going to be breaking down, making reactants. And so rather than one arrow, we're going to see a double arrow going on. And so that's one thing that we're going to see. And so what we're going to do on this video is learn how to write the equilibrium constant expression. And we're going to learn how to calculate the equilibrium constant and learn what the equilibrium constant is going to tell us. In our next video, we'll go into more complicated problems known as a rice table or an ice box, depending on which book you use. I say rice table. So again, we did this example with the kinetics where we've got the reaction A and B, C and D, and then the little letters are supposed to be the coefficient. And so when you write in an expression, it's always going to be the products raised to some coefficient power, so some power here, so some power. And it's going to be the coefficient power, so it is going to be the value that's in front here. So that's why we see little c and little c, and it's little c and little d over the reactants. So products over reactants. So, and that's going to be raised to the coefficient power as well. And that's going to get us a constant. What it does is it's a comparison between the rate constants of the forward and the reverse reaction. And so it does relate to kinetics, and I could go into and show how those reactions cancel out and how we end up getting it. So it does relate to the reaction rate constant, the little k. This is actually capital K that we're going to be dealing with. And we're going to see different variables. Well, first one we're going to introduce you to is little c. Little c means concentration. And we measure concentrations in molarity. So when we have molarities, we'll be calculating what's known as Kc. If we have atmospheres, and atmospheres is the most common one, we'll be calculating Kp. And so when you write the Kp expression, it looks very similar to the Kc expression. They're still going to be raised to the power, except you're going to have p's instead of the brackets. We're going to do some examples, so this will make more sense. And so you can come back, we'll come back to this in a moment and read this after we do our first example. All right. So it says the Haber process. This is an important process. This is the making of ammonia. The Haber process is how we make ammonia. And ammonia is such an important compound in our food production. It's in our fertilizers and stuff. So Haber came up with a way that we could mass produce ammonia. Unfortunately, it was used in the beginning to make ammunitions for the war, but now we use it for production for food. So it says write a balance equation for the synthesis of the ammonia. So synthesis is when you're making a product, and ammonia is NH3. That's a very common compound. NH3, ammonia is a gas, and we're making synthesis. So synthesis means two things come together, make one, and so we're going to get nitrogen diatomic is a gas, and it's going to react with hydrogen diatomic as a gas, and we would balance that equation by putting a 2 here and a 3 there. So there is our balanced equation. Now, because we were so used to, let me fix a couple things here. We're so used to drawing that one arrow. If we were to take nitrogen, hydrogen, get it in the right conditions, and the molecules could bump and we would overcome activation energy, etc., we could make ammonia. But in an open system, this ammonia would just escape. But if we were to get the conditions just right, we could make ammonia. Then all of a sudden ammonia would start breaking down, and we could reach a state of equilibrium in a closed system. So that's what we're going to be dealing with, is when it makes the forward reaction of making ammonia equals the reverse of making nitrogen and hydrogen. When I say equal rate, it's not equal amount. Sometimes it might be a 50-50, but not always. It could be an 80-20, 80% this and 20% this, but it's when it equals equal rates where it no longer looks like it's doing anything. So we're going to learn to write the Kc and the Kp for this. So the Kc, we're going to use molarities, but we're going to learn to do the expression. So the expression doesn't have numbers or anything in it. It just has the letters, and we use brackets for Kc. So you're going to put the product. Even though this arrows are going back and forth, we're always going to call this right side the product side. We're always going to call this the reactant side. Okay, so we're going to put product, so we're going to put NH3, and we're going to put it in brackets, and we're going to raise it to the coefficient power, which is 2. Okay. Now there is a rule with this, and we'll talk more. I'm going to go back to that page in a moment. You do this for anything that's a gas or anything that's aqueous. You don't do this for liquid, pure liquids, and you don't do it for solids, because solids and pure liquids keep a constant concentration. So gases, pressures change and molarities change of gases in aqueous environments, but not pure liquids or solids. So I'll go back to that note page in just a second. So these are gases, and so then we're going to be putting them in the expression. And so we got that, and then we're going to be putting it over these guys. So it's going to be H2 raised to the third power. I could have done N2. It doesn't matter which one goes first. Times, whoops, my board just freaked out on me. N2, and that's raised to the first power. And again, you don't have to put the ones. So that's the expression. That's the Kc expression. So products raised to the coefficient power over reactants. All right, for Kp, it looks very similar for writing, except for instead of brackets, the brackets mean molarity. You're going to use parentheses, and you're going to put P, and you would write NH3 in a subscript form, parentheses, which is going to raise it to the coefficient power, divided by parentheses P, and again it doesn't matter which one we write first, I'll stay consistent, I did H2, and it's raised to the third power, and P, pressure, and nitrogen raised to the first power. So this is called the Kc expression, this is the Kp expression. Alright, so let's go back to that note page number 1 and look at those rules. And so it says A and D are the molar concentration, so that's what we've got there. P's are the partial pressures. The products are in the numerator, and the reactants are in the denominator, so products over reactants. Coefficients in a balanced equation become the exponents, so we raise them to those powers. And this is what I'd like you to highlight, write down, because this is where students miss it. This one right here. Solids and pure liquids were ignored and do not show in the equilibrium expression. You're going to like this when we go to calculating. There are no units for the equilibrium. Technically there are, but they change so much, so we just say, well, we're just not going to worry about giving the equilibrium constant a unit. So technically there are. So let me give a generic thing and just show you. So if I had, well, I'll actually do a real one. So if I had silver chloride and I were to put it in water, it's a solid. And water, if I put it in water, it'll make some ions, and that becomes aqueous. It gets like that. And if I wanted to write the Kc expression for this, we wouldn't have a Kp expression for this one because there's no gases. So you only have Kp if there's gases. So the Kc expression, let my thing can stop. This new computer does not like my old program here, so it gets hung, so I have to wait till it gets unhung. There we go. So the Kc, and you don't have to write the little c because it's just going to be the K. It's going to equal the products over the reactants raised to the coefficient power, but we don't put solids in there. So let me show you if you did. So if it looked like this, it is silver ions and not silver solid. It would be raised to the first power, and it's multiplied by the chloride ion raised to the first power, and it wouldn't have a bottom, or you could put it over 1 because it doesn't, and so anything over 1 is just going to become itself. So if it's a solid, it's not going to be over anything. We'll learn soon, next week I think, that this is known as the KSP, solubility product. But if we had something else that looked like, I'll make this one up, A as a gas plus 2B as a gas made 3C as a solid. Okay, so we had something like that. So if I wanted the KC, we'll just stay with KC. KP looks the same because there are some gases in this one. There's no top this time because there's a solid in there. So these are real simple to use, but students will miss them because they'll put solids. So it is products over reactants, but this time our product is nothing but a solid. So we would do 1 over. See, the 1 wasn't necessary here because it was on the bottom, but we need the 1 this time. So it would be A raised to the first power and B raised to the second power for this one. I hope that makes sense. Again, super easy to do, but students will miss these because they will put the solids of pure liquids. About the only pure liquid you're going to need to worry about is water. Because, you know, we do have some other, like bromine sometimes is a liquid, Br2, but not bromide, but bromine, Br2. But most of the time we won't have pure liquids. So it's the solids that will sometimes mess students up. Okay, so our next one says, and this is uploaded for you if you want to print this out. If the concentration's at equilibrium, so I'm going to have you highlight this because that's going to be important. That right there, at equilibrium. So that means that the numbers that they're about to give me, that this system has already reached dynamic equilibrium, and I can go ahead and put these numbers directly in the expression, meaning I'm not going to have to do a Rice table because we're going to do that on our next lesson. So we're already at equilibrium, so I'm ready to go ahead and use these numbers. So it wants me to calculate the Kc. It says actually just calculate the equilibrium constant, but these guys are all molarities, so I know I'm going to calculate Kc. It would have to be atmospheres for me to calculate Kp. Okay, so I'm going to calculate Kc so I'm just going to plug these in. So Kc is going to equal the ammonia raised to the second power, and it says that ammonia is 0.01. So I'm going to have a 0.01 molar and I'm going to square that, and I'm going to divide by, it says that nitrogen is 0.02 and that hydrogen is also 0.02. So 0.02, and that is going to be cubed times 0.02, and that's going to be to the first. And then I would just put this in my calculator. I would tell you to take a second, put that in the calculator, because believe it or not, some students do miscalculate that. Okay, so products over reactants, and you should be getting 625. No unit. Technically it could have a unit. You've got m squared on top and m to the fourth on bottom, so technically it's m to the negative second. We're not going to worry about it. Okay, so for our purposes, K doesn't have to have a unit. So what this does, this number tells me something about this reaction. It tells me what's favored in this reaction when I put all these things together, what's being favored to get made. Not what's there at equilibrium, but what's getting favored to be made. And so there is a rule, and it is if K is more than 1, I'll go to the page here in a moment, but if K is more than 1, then the products are favored in this reaction, okay, in terms of molarity in this case, because K is greater than 1. That'll make more sense as we continue on. Greater than 1. We're going to see it with acids. We're going to see it with some bases. We're going to see it with some KSP. It's going to tell us which way this reaction favors to before it gets to equilibrium. Alright, K is greater than, and I want to write 1, but my board is not allowing me to write for a second because we're spinning. It does take up time when it does that. Okay, so if it had been less than 1, the reactants would be favored. If it's at 1, neither one are favored. That means they're favored equally, like a 50-50 mix. Okay, so let me go to the page where all this says. Okay, so equilibrium constant is the actual calculated value. If it is much more than 1, it means the products are favored. If it's smaller than 1, the reactants are favored. If it's at 1, then we have an equal mix of the two. So I do need you to know that. Okay? All right. So now let's look at all the different cases we're about to encounter. We're going to be seeing all different equilibrium constants. We just looked at Kc, molar concentrations, Kp, when our pressures are in atmospheres, and those are just for gases. We're going to look at Ksp, which is called the solubility product. We'll see that in our next unit. We're going to have K with a little a, that's just going to be for acids. K with a B is going to be for bases. We're going to see Kw, that's going to be for water. But the good thing about these, they all work the same way, so that we don't have to get worried about them. What we're going to worry about right now is this formula here. Okay, so this formula here is, if I know Kp and I wanted to solve for Kc and I didn't have like molarities and I didn't want to convert them all, I could use this formula. And the other way around too. If I knew Kc, I could calculate Kp without having to change everything to atmospheres. I could use this formula. So I will give you this formula. You don't have to memorize it. So if I were trying to solve for Kp, I could take the Kc value and I would multiply it by RT, and R is the ideal rate constant for atmospheres at 0.0821. You should have learned that from Chem 1. Times T. T has to be in Kelvin. That is very, very important. How do you go from Celsius to Kelvin? You add 273. So whatever your Celsius, add 273 to get our Kelvin temperature. You should have learned that in gas laws as well. Okay, and both of those are raised to delta N. And I don't know if you remember when you did PV equals nRT, the ideal gas law, which is what this is a deviation of. The N was number of moles of gases. So it's really important for us to know that this is number of moles. The little triangle means change in. Change in is always the final minus the initial. So it's going to be the moles of your product gas minus the moles of your reactant gas. And we're going to do a problem like that. Okay, so it's moles of product gas minus moles of reactant gas. Alright, so it says calculate the Kp for this reaction. Let me get that reaction back up here where we can be seeing it on this problem. So we had nitrogen plus 3 hydrogens, and that made 2. You get that double arrow. I'm going to not been doing the double arrow for a while, so I'm going to have to make myself do it again. Okay, so there's our reaction going on. We just calculated with all that information we just had, and it did say, let me go back to that problem, I think it said we were at 25 degrees. Where did you go? Yes, we're at 25 degrees Celsius. So, and we just calculated that Kc to be 625. Okay, let me go back. Alright, so we're at 25 degrees Celsius. So we're looking for Kp. So we just learned the Kc was 625. The R, we're not going to worry about putting the units on R. He's got a bunch of really pretty units, if you remember from gas laws. 0.0821. And the reason I'm not going to make you worry about units is because your case don't have to have units. Just know all the units do cancel out and it's all good in the end. Okay, so here's important. This R and T are multiplied together, and that is then raised to the power, okay? So RT multiplied together, that's raised to power before you multiply it by that. Okay, so that plus the 273 is going to give us 298 on the Kelvin scale. And then it's raised to the delta N. So let's talk about delta N power. Delta N is the products minus the reactants and just gases. So if you had some solids in there, you would ignore them. If you had some liquids in there, you would ignore them. And if you had some aqueuses in there, you would also ignore them, because we only care about gases for Kp. Kp is pressure. Pressure only deals with the gases, so we only care about the gases in this state. Alright, so over here we've got 2 moles of ammonia, but over here we've got 1 mole of nitrogen and 3 moles of hydrogen. So over here you've got a total of 2 moles, but over here there's 1 there. There is a total of 4 moles of gases. I know they're different, but as far as pressure is concerned, it doesn't matter. Okay, so you're going to have products, which is 2, minus reactants, which is 4. You're going to get a -2 power. So we're going to raise this to the -2 power. Now I would suggest you do this part, raise it to the -2, and then multiply it by 625. It really doesn't matter, but I've had students that'll do it all together and they'll get the wrong answer. Okay, so these raised to the power that, you're going to get 1.04. We'll just do 3 sig digs. Usually makes me happy. So this is really close to 1. So as far as what's favored in the pressure situation, actually they're about equally, products and reactants are about equally favored as far as pressure is concerned. Alright, hopefully you understand how to use the Kp. Alright, number 6 says calculate the Kc for the reverse reactions if we use the same molarity as before. So the reverse reaction would be now looking like this. It would look like this, and you would end up with, right. And so if we did those products over reactants, if we went back to that same problem that we were doing a second ago, I have to go back for a second, this problem, can you see that this would be flipped around? So we would have these numbers on top and that number on bottom. So I could take those and flip those around. And so I could go 0.02 molar cubed, it's 0.02 molar to the first, that's these guys, divided by 0.01 molar to the second. And I could put that in the calculator. And I would get, I actually wrote that down somewhere. Don't know where I wrote it down. Well, let me just get my calculator out. I really did write it down. So you would get 0.0016. Okay? So can you see what's being favored? That's less than 1. Ammonia is still favored, right? Because it's now the reactants being favored. So I flip this around. This is known as the reverse equation. But there was an easier way for me to do it. I did it with the actual numbers, but if I knew what the forward reaction was, the forward reaction was 625. So going this way was 625. And I asked if we reverse the reaction, if the equation's been reversed around, all I needed to do was go 1 over 625. If I just take 1, it's called a reciprocal. If I just take 1 over 625, I'm going to get the same number. Hope that makes sense. So if you know the reaction constant one direction, if they ask for the opposite direction, you just take 1 over that value. Alright, so now let's look at our original equation. There's our original equation up there. And look at the equation they're wanting me to find now. Here's the equation they're wanting me to find now. So they want me to find the Kc for this equation. And that's the original equation. I know that the original equation was 625, correct? Not this one, because that was the flipped around one. So this one is 600. This one was 625. So can you see what has been different between that equation and that? That N2 has just a 1. This has a 2. That has a 3, and that's a 6, and that's so it's been doubled, right? So I could actually go back to that original equation, change those coefficients, and calculate it that way, or I could simply say this reaction. The difference between that reaction and that reaction is a double. I could take this and raise it to whatever I do to its power. So I doubled it, so I would square it. Not just double the number. Hear me? Not just double the number, but actually square it. So I would go 625 squared. 390,625. Okay, so if we did sig digs, we won't worry about the sig digs on that, so we'll just go with that. So now it's really favored the ammonia, so I've doubled those concentrations, favoring making more ammonia. If I did sig digs, I would have to do scientific notation. Times 10 to the 1, 2, 3, 4, 5 to the 5th to get it incorrect. Sig digs. Oops, made an error. Someone's going to catch me on that one. That would actually be 1 because it was a 6 there. There we go. Now I think I got it right. So this is the correct sig dig answer there. Alright, so let's show you some what ifs. What ifs. I just wanted to do a few what if situations with this. So this is what I just said. So when we change the stoichiometric coefficient, you're going to raise it to the multiplication factor. So that's what we just did. We had doubled it, so we squared it. So we're going to look at that. If we reverse a reaction, you're going to do the reciprocal, which means to take 1 over. We'll get to this one in just a second. So let's go to that blank page that I was working on. All right, I'm going to do some generic, and normally if we were face-to-face, I would challenge you with some of these. And so if I had a reaction that looked something like this, and I said that the K for this was 200. And so then I gave you this. I'm not going to put the gases. They're all gases. We'll just say they're all gases. And I asked, what is the K for this one? Well, from this equation to this equation, I have flipped it around. So your answer, and I would actually like you to calculate it out, not just leave it like this. You would take 1 over, and that would get us 0.005 as an answer. Okay. I only have 1 sig dig there. If I wanted it to have 3 sig digs, I could do that. No big deal. Okay. So what did I do? I flipped it around. If If I flip it around, it's the reciprocal. So now if we have something like this, all gases, not that it would matter for what we're doing here, and I had the K was 0.125. What's being favored? Less than 1, so therefore reactants favored. Greater than 1, products favored. Okay? So now if I ask and I did this, and I asked for the K, so what's the difference between that one and that one? Well, it's 3 times more, right? 3 times more. So I don't just multiply this by 3. I am going to raise this to the 3rd power. Okay, so whatever change you make it, you raise it to that power. So you would get a 0.00195. That's our answer. All right. Hopefully that's making a little sense to you. And we've got some 2a plus 4b makes a C, and I give you the K equals 300. Put a dot for 3 sig digs. And I said, well, what would the equation be if I did this? Just A plus B. So if you want to stop the video and see if you can figure that out, and if you're not, then you can just let me answer it. Okay, so let's see. What's one difference between that? So first off, C is a product here, C is a reactant there, so it's been flipped around. So I know that I gotta do this, right? That's gonna take care of the flipping aspect of it. But there's been another change. This C has a 1 in front of it. Now it has a half in it. That had a 2 and now it has 1. That had a 4, now it has a 2. So this equation is half what that is. So I need to raise this to the 1/2 power. Now believe it or not, the 1/2 power is actually the square root. So you would be taking the square root. You can actually put it in the calculator like that. It'll work. You can put it in a calculator like this. That'll work. Or you could take the square root. And it honestly doesn't matter what you do first. You could take the square root, then do 1 over or 1 over in the square root. It doesn't matter. You'll get the same answers. So you get 0.0577. Okay. So if you have a reaction and you know the constant for it, if they ask for, or if I ask for a reaction, see what I've done to that reaction. Have I flipped it? If I flipped it, you're going to take 1 over. Or if I've changed the coefficient, how much have I changed the coefficient? And then you're going to just raise it to that power. All right, hopefully that makes sense. And so let's look at the last type if we ever stop spinning here. Okay, so our last type is here. Last lesson in kinetics, we were doing those elementary steps, and if you look here, you see the C's and the D's, those are those intermediates. So if you have a reaction where it goes in more than one step, to find the overall K, so for instance, if I knew the K of first step was 4 times 10 to the 3rd, and K of the second step was 2 times 10 to the 4th, all I got to do is multiply those two together. And you get 8 times 10 to the 7th, and it's as simple as that. So hopefully this makes sense, and if not, please come see me.